Right. Welcome everyone to statistics. So in this particular session, we're going to just do a brief introduction to statistics, get some definitions out of the way, and before we dive into the material from next week onwards, right? So this is not very technical. It's a brief introduction to statistics, what we are dealing with, what the basic roadmap of the course looks like, and all the attendant details to that. Okay, so let's talk about a few definitions because we need to define a few things before we can get the ball rolling on the technical details on how we do statistics in the modern world. And the first question becomes what do we mean when we say statistics, right? So in its very core essence, statistics is a science about data, right? So there's a lot of data which is floating around, especially these days. We have a lot of data available. There's this massive data collection, and we have these large data sets that we can use to inform policy decisions in the economy in general. But any kind of business decision relies heavily on collection of data and the ability to analyze and synthesize what we see in that data, right? So with statistics, we are trying to formally figure out how to collect data to begin with, then how to basically organize it, and then the part of it where it becomes very interesting. This is where the tire meets the road, is when we can begin to use the data to analyze and interpret and inform policy decisions, right? So the question then is, what do we mean by data in general, right? And data can come in any kind of many kinds of different forms. We'll talk about different kinds of data, but basically it comes from observations, measuring things, or collecting responses to certain questions, and we can catalog all the responses, and that becomes a data set, right? So we can imagine that there's different types of data. There's data which comes from surveys, where we send out a questionnaire to people and collect their responses, right? So an opinion poll is one kind of a survey data. So in the news, when you see, okay, that Joe Biden is leading in one particular state or nationwide or whatever, we're not talking to everyone in the nation or in the state. We're talking to a subset of the people there and collecting their responses, right? We're sending out a survey and asking them, do you view this candidate favorably or not? Why do you think so? And so on and so forth, right? Data can also come from what we call randomized control trials. This is particularly used to be the bailiwick of pharmaceutical data collection in general. We'll talk about what a randomized control trial is, and why it's the gold standard for data collection in statistics right now. And for the most part, we are trying to collect data using randomized control trials as much as possible these days, right? It has a very nice feature to it. We'll talk about it in just a second. But we can get data from these kinds of trials, randomized control trials. Right? We can also collect data in census. Right now, the census operation is in full swing in the US. Every 10 years, we collect data on basically to get a snapshot of the entirety of the population of a country, and that informs how much each county gets funding from the federal government. How do we divide up electoral college votes? How do we draw districts for electioneering purposes? How do we make sure that social security benefits and unemployment insurance benefits and so on and so forth, how do we manage for those things? All of that is informed by data which is collected by in a census, right? So that's where we collect macroeconomic data around unemployment, around the health of the middle class, and so on and so forth, right? And then we can also think about data as primarily we collect two kinds of data, right? This is not exclusive, but this is dominantly the two kinds of data which usually we end up seeing, right? The first kind of data that we see is cross-sectional data, right? As the name suggests, it's a cross section, which is to say we freeze time and take a snapshot of the snapshot in at that particular moment in time. So we want to observe what is happening at a single moment in time, and then figure out what the data that we're collecting at that point in time has to say about the state of the world at that point in time, right? The other kind of data that we might often see collected is what we call time series data. And with time series data, we were more interested in knowing about the evolution over time, right? We want to observe the same individual or the same observation or the same unit of observation at different points in time, and that tells us how the information is evolving over time, how the data point is evolving over time, and that gives us an indication of dynamics, right? How things are changing over time. Are they getting better? Are they getting worse? Right? For instance, one classic kind of this is around infant mortality, right? So we want to know whether advances in medical science and in public health are actually helping the population, and one measure of this is to figure out how what proportion of infants that are born survive into adulthood, right? So we want to make sure that over time, what is the infant mortality rate? If it's falling over time, that's a good sign that more and more babies who are born are surviving into adulthood. There's not a lot of death in childbirth, and that gives us an indication that public health measures which are put in place to make sure that that's the policy objective is actually working, right? We are collecting the same information, which is infant mortality, at different points in time, and we are observing how that particular variable is evolving over time, right? So usually we might have like purely cross-sectional data or purely time series data, and sometimes it's a mix of both of these things, which is what we call panel data, and then things get a little bit more complicated when we do analysis, right? So at least in its basic form, we usually either deal with cross-sectional or time series data, and there are different techniques, different econometric techniques that you can apply to analyzing different kinds of data. Not all kinds of data can be analyzed using the same kind of techniques. There is an entire body of work devoted to studying time series analysis, and there is an entire econometric treatment of how do we deal with cross-sectional data. Okay, so again, this is a basic introduction. So if you want to look at a real world example of how we collect data, there is Gallup, which is a polling firm which collects this data or conducts a survey which is called the Gallup Daily Tracking Survey, right? So what is the goal of this survey? So what Gallup wants to know is that they want to understand how attitudes and behaviors are changing in America over time, right? And they want to continuously collect this data so that they have a fine-grained analysis as to how issues or how attitudes or behaviors on particular policy issues are evolving over time. And the way they do that is that, it's obviously impossible every single day to talk to all the people who live in the US. Ideally, that's what you would want to do, right? You want to talk to every single person, ask them the same question, and collect their response. But instead of doing that, what they do is that they randomly survey 1,000 US adults each day, right? So 350 days out of the year, they're going to do this survey. So they're going to send up randomly survey 1,000 US adults. It's who gets to be in the survey is completely random, and they ask them different questions about what do you think about the state of the economy, what do you think about the government, what do you think about some key button policy, social issues, right? What do you think about, the abortion debate? What do you think about gay marriage, so on and so forth? This is just a way of making sure that we can collect data on how attitudes and behaviors are changing, right? And earlier in its original incarnation, Gallup has been doing this for a long time, and they used to basically do random dialing, right? So you have phone numbers, landline numbers for a lot of people who live in the US, and then the computer just picks out 1,000 of these numbers at random, and then the surveyor just dials up these numbers, asks them if they want to participate in the survey, and if they say yes, they collect their responses, right? Now it's also obviously not a lot of people have landlines, so now we have also data on cell phones, so that's how they collect this survey, using some random digit dial methods, right? But as you can imagine, if you're talking to 1,000 random US adults every single day, the data set starts to get very large very quickly, right? You're going to collect very large sample sizes, right? In each week, you're going to collect some 3,500 odd units based on the responses, right? So the response rate is not going to be very high in these kinds of things, as you can imagine. If a random person calls you up and you're in the middle of something and says, do you want to participate in a survey about this thing or the other thing. A lot of people might say no, but they keep dialing till they get a sufficiently large enough sample, and pretty soon you can have like a very large sample of these data points, right? So this gives us a nice little data set to analyze demographic trends, about trends around social issues, about attitudes, behaviors, and so on and so forth. And this is one example of what a modern survey data collection looks like, right? Okay, so let's talk about a few definitions. I mean, some of these definitions are fairly obvious. It's not particularly complicated, but we need to make sure that we understand these definitions before we can dive into the technical aspects of studying statistics. Okay, and one key thing, key set of definitions that we need to know is the difference between a population and a sample. Okay, so a population is, as it suggests, it's a collection of data where we are collecting data on all. The crucial word here is all. So we are collecting every single data from every single a person or entry inside that defined population. The population can be defined in any way. It can be defined in a very expansive way, or it can be defined in a very constricted way. But the crucial thing is that once that population is defined, whatever you define as the population of study, if you're going to collect responses from every single unit of that population, then we have what we call the population data set, right? So for instance, if you want to understand the income, if you want to know what the income is of all US adult citizens, then that is the population, right? You have to find every single US adult, ask them their income, record these responses without errors, and then you have a population data set. As opposed to what we call a sample, right? Once you've defined a population, any smaller set, any subset of that population is defined as a sample, right? So with the sample, we are not collecting data on all the units which constitute the population. We're going to collect information only on a smaller subset of it. For instance, if you collect only data on the income of US adult citizens living only in New York State, now New York State, all the people who live in the New York State are a subset of the entire population, adult population of the United States, and so that data that we collect from that process is what we call a sample data. So a sample, as you know, here's a clean diagram that represents it. The population is always going to be the larger unit of interest, and any smaller subset of that population that we've defined is what we call a sample, right? So depending on whether we have population data or sample data, the statistical techniques that you can apply are going to vary slightly. We'll get into those technical details later on in the course, but that's one thing to keep in mind as to when you have a data set that comes in, the first question to ask yourself is that, is this a data set about the population as a whole? Do we have information on every single unit that is defined in the population, or do we have information only on a small subset of that unit? If it's the latter, then we have to apply statistical techniques that apply to sample data, and if it's the former, then we can apply statistical techniques that are applicable on a population data set. Okay, so here's a quick little example of how we distinguish between populations and samples. So in a recent survey, we conducted a survey, 1,500 adults in the US were asked if they thought there was solid evidence for global warming. 855 of the adults said yes, and we want to figure out what is the population and the sample. Okay, so now what are we trying to do? We are trying to figure out what do people in the adults in the United States, what is their view on global warming, right? So the population here consists of the responses of all adults in the US, right? That's the largest set. We want information on what the attitude towards global warming is for every single person, every single adult who lives in the US. What we have here, however, is a subset of all the adults who live in the US. We only have information from 1,500 adults who are living in the United States. So we have a small subset of that entirety of that population, right? So the sample here consists of the responses of the 1,500 adults who actually responded to a survey, and that forms a smaller subset of the underlying population, and this is what we call a sample data set. Okay, and then if you want to go a little bit further, The data set obviously consists of 855 people said yes, that they think that there was solid evidence of global warming, and the remaining 645 people out of the 1500 people we talked to said no. And then you have a little description of that sample data set. But the crucial thing is here to understand that this here, the data that we collected is only for 1500 adults in the US. We are not collecting a response from every single person in the country, and that if we had, that would be a population data set. But in this case, we are only interested in the responses of a smaller subset of that underlying population, and so we have a sample data set. Okay, so it's important, crucially important, to basically draw that distinction between whether we are dealing with a population data set or with a sample data set. Okay, the second key sets of definitions is that between what we call a parameter and a statistic. Okay, a parameter is basically anything that if we measure something about the population, right, a numerical description, any number which describes some population characteristic, that is what we call a parameter, right? So there's a nice alliteration here. So if it's a population, if you're measuring something about the entirety of the population, if it's a numerical measurement about the entirety of the population, then we call it a parameter. So it's a population parameter, so P and P. So for instance, if you measure the average age of all the people in the US, so we are measuring something about the entirety of the population, and so this would be a population parameter. Okay, as opposed to a statistic. Right, a statistic is something, a measurement, a numerical measurement about a sample, right, a smaller subset of that population. So if I collect information on the average age, if I calculate the average age of all the people who are living in New York State, that's a subset of the entire population of the United States, and so now I have a numerical measurement about a sample, and this is what I call a statistic. Again, there's an alliteration there, so sample, statistic, S&S. So that gives you a clean way to remember these things, that if I'm measuring something about the entirety of the population, then I call it a parameter, and if it's something about a statistic, if I'm measuring something about a sample, then I call it a statistic. Okay, and it's important to keep those distinctions in mind, because the end goal in statistics is to basically use this statistic, something that we measure about the sample, to say something worthwhile about the population parameter, right? All right. Here's a few quick examples for you to figure out whether you're dealing with a population parameter or with a sample statistic. Okay, so let's figure out. Here's the first example. So a recent survey of a sample of college career centers reported that the average starting salary for petroleum engineering majors is $83,000, 121 cents. Okay, so what kind of measure is this? Is this a measure about a sample, or it's a measure about the population? And in the statement itself, there's the clue, right? The survey didn't survey all college career centers. It only surveyed a small subset of all college career centers. So it surveyed only a sample of the college career centers. So what we have here is a sample statistic, right? The average that we calculated, the average starting salary for petroleum engineers that we calculated of $83,000 and $83,121 is a measure which is calculated from a subset of the overall population, right? What is the overall population here? The overall population would be to collect information from all college career centers and then calculate that average. Then you would have a population parameter. Okay. Second example, the 2,182 students who accepted admission offers to Northwestern University in 2009 had an average SAT score of 1442. Is this now a sample statistic or a population parameter? And straight away you can see what is the population. Now the population is not all the people, all the college students in the country. That's not the population of interest. The population is very narrowly defined. We are only concerned with all the students who accepted admission offers to Northwestern. and what we have is that 2,182 students accepted admission offers to Northwestern. So we have information on every single one of those 2,182 students. So the population, which is narrowly defined here, is all the students who accepted admission offers in the US, and we have responses. We know the SAT scores of all of them. Then the average SAT score that we calculated here is now a population parameter, right? Because the average SAT score that we calculate here is based on all the students, right? We have information on every single unit that is part of this population that we've defined, right? So it's important to keep this distinction again in mind, the difference between a population and a sample, and the difference between population parameter and sample statistic. Okay, all right. With statistics in general, we try to draw this distinction between what we call descriptive statistics and what we call inferential statistics, right? So when we talk about descriptive statistics in general, there is nothing analytical about it, right? So what we're trying to do is that we get the raw data, we go out into the world, collect a bunch of data, and the first order of business is to take this data and begin to organize it in some meaningful fashion, right? So with descriptive statistics, we're just basically trying to get a picture of what the data set has some key features and characteristics. We're just basically trying to describe what we are seeing in some meaningful way, and that's the entire branch of statistics devoted towards that part of it, right? So it's about organizing, summarizing, and then maybe some data visualization, some displaying data, and that basically gives us an indication of the fundamental behavior inside that data set. Okay, so in this course, that's what we'll do. The first few weeks of this course is devoted to understanding some descriptive statistics techniques. How do we use these techniques, and how do we create these tables, charts, and averages and graphs, and some key summary statistics to basically describe the data, to give us an indication of what the data set itself looks like. But that's interesting and that's a useful exercise, but the power of statistics lies in drawing inferences. Okay, and so that's the branch of statistics which is the most involved. That's where the power of statistics comes from. The inferential part of it is basically derived from the following reasoning, right? Suppose I want to study the entirety of the US adult population now, or let's say the entirety of the US population. Now there's about 330 million people, plus or minus a few million here or there, roughly about 330 million people who live in the United States. So it's going to be virtually an impossible task for me to, for every single small question that I have, for me to go around collecting responses from 330 million people on every single issue, right? It's just humanly impossible. It's going to take a very long time for me to do that. In the ideal world, yeah, that's what I would like, because I would like to collect the response of every single person who lives in the US. But more often what we deal with is to say, okay, studying the entirety of the population is very, very cumbersome, very difficult, very time consuming. It consumes a lot of resources in order for me to do that. So instead, there is a workaround that problem. And what is the workaround? What we can do is to collect a sample of that population and use that sample to study the entirety of the population, stand in as for the entirety of the population. The so-called the holy grail in statistics, the so-called representative sample, right? So if you want a brief, kind of a mental picture, it's a useful metaphor to keep in mind. So if I want to understand the basic characteristics of ocean water, right? How much salt is there, how much silt is there, what kind of composition is there in the ocean water. Now I don't have to study every single drop of the ocean water. If that is what I had to do, because if I had to study, that would be my population of interest, is all the ocean water that there is. If I went about doing this, where I collect all this, collect drop by drop of this ocean water, and then begin to analyze it, now it's going to take many lifetimes for me to finish that. I might never even finish that job ever, even if I had 20 lifetimes. But instead, if I collected a sample, if I just went to the ocean, collected a glass of water from the middle of the ocean and brought it in for analysis, now in a fundamental sense, what I have is a sample of the overall population. But if I can understand that sample in depth, I might be able to very to a great degree of precision understand the entirety of that entire characteristic of the underlying population. And that's a useful metaphor, because there is what we have here, because ocean water is very homogeneous in the sense that it's the same everywhere for the most part. It might have big differences here and there, but if I go to the middle of the ocean and collect a sample, I'm going to that sample is going to be sufficiently close enough to the underlying population, to the underlying ocean water, that I can be reasonably confident in if the salinity, if the amount of salt content in that sample I collected is, I don't know, 20% or whatever, I can reasonably make a guess that the ocean water as a whole has a salinity level of about 20%. Right? I can make those guesses that way. So the crucial part of that is that the sample we have collecting, right, the sample we are collecting out of the population needs to closely match in fundamental ways the population that we are interested in studying. That's what we call a representative sample, right? So if we can find a representative sample of the underlying population, then that's usually enough, right? If we study that sample in a lot of depth, then whatever analysis and whatever understanding that we get out of that studying that sample can be used to inform what we want to know about the larger population. And that's what inferential statistics is trying to do, is to collect sample data and use it to draw conclusions about the entirety of the population. Okay. Again, a couple of other definitions that we need to get out of the way. There's difference between qualitative data and quantitative data. So the big difference is that when we talk about quantitative data, we are talking about numerical measurements or counts, right? Anything which is measured in the form of numbers, numerical measurements, or anything which is counted, then what we have there is a quantitative data set. Okay. Qualitative data is data which is non-numerical, right? And it's about labels, attributes, so on and so forth, right? So if you think about this data set that we have here, where we have the names of these cities, so that's one kind of data, just collecting labels and names, so we know what each of these places is called. And then we are collecting information on the population in each of those cities. This is quantitative data. This is numerical measurements versus qualitative data. Okay, so that's one difference. Quantitative data, when you hear someone say they work with quantitative data, what they're dealing with is with measurements and counts. Anything which is numerical is what we call quantitative data, versus anything which is just a label or an attribute, anything which is non-numerical but still is describing some key feature about the object of study, that's what we'll call qualitative data. Okay. There is again what we call levels of measurement. There is what we call the nominal level of measurement and the ordinal level of measurement, where we have nominal data sets and ordinal data sets. Nominal data sets are purely descriptive or qualitative, right? There is no mathematical computations that can be derived on this level of data, right? So for instance, if I have a list of all the names of the people in my class, that is basically a nominal data set. There is no mathematical computation I can do where I can order this data set in any particular way, right? An ordinal level of measurement, however, allows us to order the data, right? It can be either qualitative or quantitative, but the data at this level of measurement can be ordered or ranked in a meaningful way. That's the crucial element of it, is that if we can take that data and then begin to order it in some kind of fashion, either using some numerical metric or some other metric, if you're able to begin to order it in some fashion, then we have what we call ordinal data. Okay, So if you think about the list of the top 10 grossing movies of 2016, that is ordinal data because there's a particular order, right? So if where you show up on that list matters, right? Because if you show up in the first position, then you are the highest grossing movie, and if you show up in the 10th position, you're the 10th highest grossing movie. So the order in that data set matters. The order in which these data points appear matters, and then we have what we call an ordered data set. Okay, an ordinal level of measurement. So the big key difference between ordinal level of measurement versus a nominal level of measurement is the question as to whether this data can be ordered in some meaningful way, right? If the order in which they appear has some inherent meaning, conveys some information, then we say we have an ordinal level of measurement. If it doesn't, then we have nominal levels of measurement. Okay, all right. The last bit that I want to talk about in this session today is to talk about data collection and experimental design, right? What are the basic elements of how we do statistical analysis in general? Okay. So we'll talk about how to design a good statistical study. What are the key elements of good design? How do we collect this data? What kinds of data can we collect? If you have to conduct an experiment, how do we design an experiment? And if usually we can't study the entirety of the population, so in general we rely on collecting a sample of the underlying population and using it as a stand-in for the underlying population. So how do we create a sample? What techniques can we use to create a sample? And how do we identify whether a sample is a good representation of the underlying population or not? If it's a representative sample, or is it a biased sample, right? How do we identify whether we have a biased sample on our hands? Okay, so let's talk about how to design a statistical study, and there's a 6-step process, and it seems fairly reasonable, logical way to conduct a statistical study. Okay, the first thing before we start off a study is to define what is the population that we want to study. So we want to set the boundaries on what we define as the population. What is the object of interest, the largest macro object of interest for that study, right? That's the first thing that we would like to identify, the population of the study. And then we would like to understand what variables of interest there are, right? So we want to know about this population. What is it that we are after? What is it that we like to know? Once we know that this is the population that we wish to study, then we want to define what key variables that we want to study. Do we want to study the income? Do we want to study age? Do we want to study some other characteristic of that population? So we need a list of all the variables that we would like information on from this population. Okay, now we have this idea, so we know what we want to study, what is the object of study, what is the population that we want to study. We have a list of variables, list of information that we want from this population. Then the next step is to go collect the data, right? We want to collect data on for this, and you want to develop a very detailed data collection plan, because if the population is very narrowly defined, then you don't have too much of an issue, right? Like in the example where we talked about the 2000 odd students who accepted admission offers to Northwestern, if that is the population that I want to study, that's a fairly simple process. All I have to do is talk to these 2000 people, collect their responses on all these variables that I want to collect. So I don't just want to know their SAT scores, I might want to know their age, I want to know where they come from, where they went to high school, what their high school GPA was, what their parental income is, so on and so forth. Or I have all these key variables of interest. And if my population is very narrowly defined, I don't have much of a problem. I can just go collect all of this data that I want and then put it into a spreadsheet, and now I have a nice little data set, and then I can conduct my analysis on that data set. However, the problem arises when we might have a very large population, right? Suppose I want to not know just about Northwestern, but I want to know about all the students in the US, and that's a large number of people, literally millions of people in colleges and schools, and it's going to be enormously difficult for me to do that. So instead, in that case, I might want to just collect a sample of these college students, of all the college students in the US. I might want to collect just a small sample of that and use it as a standard. Now, the crucial element of this, if you're going to use sample data, is to make sure that the sample data is representative of the underlying population, right? So, for instance, if you can imagine, suppose um, the suppose there's 50% of all college students are men and 50% of all college students are women. Okay, suppose that's what the distribution is in the overall population. Now, if I collect data, if I collect a sample, and I talk to 100 college students, that's my sample, and 80 of them are men and 20 of them are women. Now that means that in my sample, 80% of my sample is men and 20% of my sample is women. That's not a representative sample. In the underlying population, it's 50-50. So ideally, in my sample, I want 50% men, 50% women, right? So the question, that's a simple enough thing for us to understand that if you're going to use a sample as a representation of the underlying population, then that sample better be representative, otherwise we will get very biased results, and then we can't rely on that sample to inform us about what the population parameters are. Okay, once you figure out whether you're going to do a population study or whether you're going to do a sample data collection exercise, third thing is to go collect that data, right? Just go get out there, collect the data, record it without errors, then bring it in, and then we can begin to study this data set. The first thing we would want to do, which is what we will do for the first couple of weeks of this course, is to talk about descriptive statistics. Once you have this data that you've collected, it's a jumble, right? You just collected data randomly in a haphazard fashion, and the first order of business is to begin to sort and organize this data into some meaningful, some coherent fashion, so that we can understand at least some key features, identify some key features of this data set, so that gives us a flavor for what that data set looks like. Okay, now once we have a basic understanding using descriptive statistics of what the data looks like, then we can move on to the next step and start using that data set to draw inferences about the population. So we have all these techniques in inferential statistics where we can use data that we collected using a sample and use that to say something meaningful about the entirety of the population, right? So that's the next part of the business, is to basically use inferential statistics to draw inferences about the entirety of the population, and then we identify any errors or biases in the study. So if there's some obvious problems with this analysis, then we go back to the drawing board. We'll see where the problem is arising from. Is it a problem with the sample that we are using? Is it a problem with the techniques that we are applying to this data set? And then if there is any biases and errors in the study, then we need to start correcting for those. And then it becomes an iterative process, right? It's not a one-shot thing. Then once you identify any errors or biases, then you go back to the analysis, go back to the drawing board, and then start over again, right? So that, in a very simple sense, is these 6 steps that you would want to do in a good statistical study, but each of these steps is fairly complicated, right? It seems simple enough for us to, when I present it to you in this clean diagrammatic way, it seems like a simple enough recipe to follow in order to get a good statistical study out. But the point is that each of these steps is fairly complicated, right? So how do we know whether the sample is representative or not is a big question. How do we collect the data? How much time is it going to take to collect the data? Once we have that data, is the data collected without errors? What do we do about missing entries in the data set? It is a very cumbersome process, but if this is a big roadmap to keep in mind, right? That if we are able to do these 6 steps in a coherent, logical fashion, then we might have the elements of a good statistical study on our hands, right? The basic elements of that are in here. Okay. So what kind of data collection, what kind of study you want to do depends on what kind of situation you're faced with, right? So we can think about different cases. Like the first kind of thing, study that you can do, first kind of statistical study that you can do is to just do observational studies, right? So in an observational study, all you're trying to do, as the name suggests, is to just observe and measure characteristics of interest of a part of a population, right? So you're not trying to actively intervene or change anything. You're just going out into the world, observing what you're seeing in the world and recording it without errors, and then you have the elements of what we call an observational study, right? So, for instance, if you want to know, right, like researchers want to observe and record like the mouthing behavior of non-food objects in toddlers, right? Toddlers, they want to understand what kind of objects toddlers are drawn to, why they're drawn to these objects, and uh, uh, why they're drawn to these objects, and so on and so forth. And the obvious way to do this is to bring in a bunch of 3-year-olds, put them in a room with a bunch of different objects and observe what happens. You're just basically a neutral observer and you're recording what happens, and that's one kind of study you can do. And based on your observations, you can tell us something interesting about what this mouthing behavior of toddlers looks like. Okay. Another kind of study that we can do is an experiment, right? So this is a more active kind of study where you want to conduct some kind of an experiment, create conditions that don't occur naturally in the world, and then use those what happens next to inform some kind of inference about the population, right? So an experiment, so suppose someone makes a claim, right? A pharmaceutical company says, okay, so we find that we think you have a hunch. Let's put it in very stark terms. You have a hunch that maybe a cinnamon extract can control diabetes. Okay. Now, how do you figure out whether that's true or not? You think it might be true, great, but just the hunch is not good enough for us to go prescribing cinnamon extract to diabetics to control diabetes, right? So what would you do? You would say, okay, so to see whether this works or not, you would want to conduct an experiment, right? So you essentially an experiment where you give a bunch of people the cinnamon extract, measure their level, see if there is any improvement in their condition after they've taken extract, and compare it to a control group which didn't take anyone, right? So you bring in two groups of big group of people, and one group of people, all of them are diabetics. One group of people, you put them on this regimen of cinnamon extract. The other group of people, you don't. And then after a few weeks, you observe whether there's a difference in their, in the lab, if there's improvement in the group which was taking the cinnamon extract versus relative to where the control group is, right? This is another kind of study you might do, an experimental study where you apply some kind of treatment, to one part of the population, and then examine whether that treatment has the effects that you predict it should have. Right? This is another kind of statistical study that you can do. The third kind of study you might do is a simulation study, right? Where you collect data from simulations. Right? So usually it's about when it's not possible to conduct an experiment in the real world, in real world situations, then you might want to simulate inside a lab conditions as close that mimic as close as possible the real world, right? So for instance, when we can't collect real world data, so suppose automobile manufacturers, car manufacturers need to know how safe their cars are, right? Consumers who want to go buy cars need to know how safe these cars are. Now if we have to figure out whether a car is quite safe or whether there's a lot of risk involved in getting into this car, how do we figure this out, right? We want to know how the car would behave if it's in a crash, right? Now if you think about it, we can't conduct this experiment with real people in there, can we? Right? Like we can't just put a bunch of people in your new car and then start crashing the car and see if the people in the car survive or not. It's not possible for us to collect data in the real world this way. We can't do the real world data collection. If you do this, you'll have a massive lawsuit in your hands before you know it. So instead, what do automobile manufacturers do? They make these dummies which have very similar characteristics to the human body. They mimic human anatomy very closely, and they put these crash test dummies inside these cars, and then they crash the car and see what happens to the dummies, and that gives us a close simulation of what would happen in the real world. It's not exactly the same, right? It's not, might not be exactly what happens to the human body in a crash, but it is close enough, right? We can study using simulations what the effect of these crashes are, right? So that's another kind of study we can do. We do simulation studies when it's not possible to collect real world data, so we try to mimic real world conditions as closely as possible and then collect the data from those kinds of studies and see what happens. Okay. Another kind of data collection process that we can do is what we've already talked about, is to just like survey data, right? This is the most common kind of data that we find, is that where if you want to know what people think about any number of things, we just go out and talk to a bunch of people and ask them, what do you think about this thing, right? So you commonly done by interviewing these subjects, or you can take internet polls, you can call up on the phone, or you can mail them a survey and ask them to fill it out. You can do any number of things. We've talked about the Gallup daily tracking poll, which is conducted using on the phone through random dialing of landlines and cell phones. So we could do that, but survey data is very easy to collect, right? If you're interested in any particular issue, this is the easiest form of data collection that you can do. If it's human subjects, all you have to do is to go ask a bunch of people what they think, and then if the people that you talk to are closely representative of the entire population that you wish to study, that's good. Then you can get on to the next business of analyzing the data and interpreting what you're seeing in that data set. Right? All right. So here's a few examples. In each of these cases, we want to consider what kind of data collection is appropriate, what kind of statistical study is appropriate. Okay, so let's think about the first one. The first one is the study of the effect of changing flight patterns on the number of airplane accidents. Okay, so what kind of data, what kind of study would you like to do, right? So we can't do just an observational study, because airplane accidents where two airliners crash into each other are very, very rare. We're not going to have a large enough data set for us to do anything like that. So we can't do an observational study, right? In that sense, we can't do an experiment, because what we would like to do in an experiment is fill planes full of people, change flight patterns, and see what happens when airlines crash and how many people die. That would not work. So this is a classic case where you might want to do a simulation, right? You would want to run a computer simulation where you change flight patterns on a computer, see if that changing flight patterns increases airplane accidents, and then what happens in those situations. So that's the case where the appropriate study is to do a simulation. Okay. Study on the effect of eating oatmeal on lowering blood pressure. Suppose you think that eating oatmeal, you have a hunch that eating oatmeal might lower blood pressure. How would you go about doing this? This is very straightforward. You can just do an experiment, right? You can bring in a bunch of people, make some of them, put some of them on an oatmeal regimen, make sure that the rest are doing whatever they were doing as they were before, and see if there's an improvement in the group that was given oatmeal versus a group that didn't, right? If there is a significant improvement in the group that was put on the treatment, in the treatment group, then we know that eating oatmeal might have a significant impact on lowering blood pressure, and then we can do an experiment and figure this out. A study on how 4th grade students solve a puzzle. So what kind of data and what kind of study you would want to do? This is a classic case where you might want to do an observational study. You bring in a bunch of 4th graders into a room with puzzles, and then let them go and work these puzzles out and see how well they do, how long they take to do it, how do they react when they meet when there's an obstacle in the way. Do they give up easily, and so on and so forth. So you're merely going to observe this behavior, record what behavior you're seeing, and use that to say something about the average 4th grader. Okay. A study of US residents' approval rating of the US president. So you want to know about people's attitudes and behaviors. This is a classic example where you would just go do a survey, right? So you can go ask people and about, the question, do you approve of how the president is handling his job? And then you can collect these responses from a survey of people, and then use these responses to tell us something interesting about what people think about whether the president's doing a good job or not. Okay. All right. So suppose we want to do an experiment, right? There's some key elements of what we would like to see inside of an experimental design, right? There's 5 key elements that we want to talk about, or 4 key elements, sorry, that we want to talk about. We want to talk about control in the experiment, randomization in the experiment participants, the sample size, and replication. Okay, so let's take each of these in turn. So when we are conducting an experiment, the first thing that we would like to do is to control for what we call for effects other than the one that is being measured. Okay, so what is it? So there is a common problem when you're conducting an experiment. Okay, this is a problem that which we call the problem of confounding variables. It's just a fancy way of saying we want to measure, suppose it's the question on, okay, does eating oatmeal lower blood pressure, and we want to conduct that experiment. Now a lot of things can be changing at the same time, right? So suppose you get a bunch of people, give them oatmeal. Now these people might be exercising, they might be changing their, because they realize that there is an experiment, they might change other behaviors in their life, and so on and so forth. Now the problem is that a lot of other variables, the real world is very messy, and a lot of things are changing all at once. We are only interested in knowing whether changing one of these things is having an effect or not, but we can't really know that because 20 other things might be changing all at the same time, and we need a mechanism in which we control for all of those other things change, right? So that's the problem of confounding variables, when the experimenter cannot tell the difference between the effects of different factors on a variable, right? For instance, a coffee shop owner remodels her shop, right? They remodel her shop, and at the same time a nearby mall has its grand opening. Now if the business at the coffee shop increases, is it because the coffee shop owner remodeled the shop and the shop looks much nicer, so that draws in more people? Or is it because there is increased foot traffic because of the mall nearby, and all the people who go to the mall, they want a coffee, they start showing up at your thing, right? Can we dissociate what portion of the new customers who are walking in because they like the decor of the new after the new remodeling, or they're just walking in because there's a mall in the neighborhood and all the traffic is flowing through into your coffee shop? So there is there's a problem of confounding variables here, where we can't disassociate things, right? So the other kind of problem that we might face ourselves with is what we call a placebo effect, right? This is particularly well documented in pharmaceutical studies, where you want to study whether a particular drug is an effective treatment or not. Okay, so you bring in a bunch of people into your study who are suffering from a particular disease, let's say diabetes, and you have like a new drug which you think will help in the treatment of diabetes. Now some people might just start feeling better. This is diabetes is one thing, is still objectively measurable. This is particularly a problem in pain medication, right? So suppose pain is a very subjective thing. There is no objective scale on which you can measure the level of pain someone says they feel, right? Because pain is self-reported, right? If I ask you how much pain are you in, you are going to give me a subjective answer. There's no objective way for me to say, oh no, your pain level is 2. You might say you are feeling a pain level of 10 on a scale of 10, you might say 10, there is no way for me to really say, oh no, your pain level is only 2. There's no objective scale. So in like a placebo effect is a problem where people start reporting feeling better just because they're part of the study and they have not received any medical intervention. Some people just start to report feeling better just because they think that they're getting treatment, when in fact no medical intervention has actually been done, right? And that's a big problem, right? So you don't know whether your drug works or not if whether when you bring in a bunch of people, whether you're dealing with a massive placebo effect where people are just reporting feeling better when objectively they're not getting any better, versus whether the drug is actually performing as advertised and as it's supposed to, and then we can go in for a larger deployment of this drug, right? So one way that we control for this placebo effect is by a technique which is called blinding, right? Blinding is a technique where the patient doesn't know whether they're part of the treatment group or the control group So in general, how we conduct pharmaceutical trials is to bring in a bunch of patients, assign them randomly, some of them to the treatment group where they receive the drug, the other group does not get the drug, and they're part of the control group. So if the drug actually works, if the people who are in the treatment group actually show a marked improvement over the patients in the control group, then we can be reasonably confident that the drug actually works, right? So blinding is a way of avoiding this placebo effect, is to not tell the patient whether they're receiving the treatment or just a placebo or just a sugar pill, right? A double blind experiment, this is a even more severe way of making sure that there is not any of these biases that creeping into the study, is where the experimenter also doesn't know whether the patient is in the treatment or the control group. So not only does the patient not know whether he or she has been assigned to to the treatment or the control group, the doctor or the experimenter doesn't know whether who is assigned to the treatment or control group, right? So again, this makes sure that there's no biases. The doctors have a vested interest to make sure that they want to see the treatment succeed. So they might, if they know that the patient is part of the treatment group, there might be some bias creeping in where they report that the patient's getting better, but when objectively the patient might not be. So in order to avoid that kind of confounding variable effects, then there is a technique that we employ which is known as double blinding, where neither the experimenter nor the patient know whether they're part of the treatment or the placebo group. Okay, so that's one key element of experimental design, is to make sure that we control for these kinds of confounding variables and biases that we might encounter. Okay, another technique which is employed in order to make sure that this level of bias is minimized is through what we call randomization. Okay, so there's very different kinds of randomization. So in its basic form, randomization just means that there is no set pattern in which people are assigned to treatment or control groups, right? The assignment is completely random. So in a completely random design, the subjects are assigned to different treatment groups through completely random selection. So one example of how I would do this is maybe toss a coin. If it comes up heads, the patient goes into the treatment group. If it comes up tails, the patient goes into the control group, right? This basically takes the experimenter's biases out of the equation. So they have no say in who gets to be part of the treatment group and who gets to be part of the control group. It's completely by random luck, by random design. Okay, now that might work in a lot of cases, but might not work in some specific cases. So you can think about another a better technique could be a randomized block design. So randomized block design is the case where we divide subjects who have similar characteristics into what we call blocks, right? And then within each block we assign people to the treatment or the control group at random, right? So with the randomized block design, what we're trying to do is that, okay, so here's an experiment. So suppose there is a new drug, right? And the experimenter wants to know whether the drug is effective or not. Now, there might be a question that there might be different reactions, that older people might react to the drug in a different way than younger people, right? So if that is a concern, then we don't want to just randomly assign all patients to a treatment or the control group. We want to put these patients into different blocks first, like, okay, young people, people under the age of 40 in one block, and people over the age of 40 in the second block. Now within each block, then who in the group which is under 40, who gets the treatment and who's in the control, again we can do a randomized design then, right? We within that block, we are not going to choose who is going to be in the treatment and who's in the control. That is going to be completely randomly assigned, right? But now we are able to understand whether there are differences between the blocks, right, between these different groups that we've assigned, and then we can understand if the drug is more effective in older people relative to younger people, and so on and so forth. Okay. Another kind of popular study is what we call match-based design, right? This is where we are trying to match people in the treatment and control group as closely as possible, right? And which makes complete sense that you would want to do that, because you don't want your control group to look very different, like markedly, remarkably different than your treatment group. You want them to be as closely matched as possible, so that gives you greater confidence that whatever is happening in the treatment group is happening because, not because they are fundamentally different than the control group, but rather because of the intervention that you're carrying out. Okay. So a very popular version of this is what we call twin studies, right? So twins are alike in a huge, in many observable characteristics, obviously, but also in underlying genetic characteristics for the most part. So the holy grail is to find pairs of twins where one twin is assigned to a treatment group while the other twin is assigned to the control group. So now we have the two groups, the treatment and the control groups, are so closely matched on many dimensions that if the treatment works, we can be reasonably assured that the treatment is working because of the intervention and not because of some fundamental differences between the groups. Okay. So match-based design is a very nice technique that we can employ. It's very hard to do a very good match-based design because in nature, as in the world, it's very hard to find like very close matches. People are very different from each other in general, so it's very hard for us to do this. But if you're able to do it, then that's a great technique to employ. In certain contexts, we might be able to do that, and that's a great technique that we can employ. Okay. The third part about experimental design, right, is around sample size, right? Sample size is very important because sample size basically determines what level of confidence we have in the results of the study, right? So if you want to, for instance, if we want to test a vaccine against a strain of the flu, or now let's say the coronavirus, we want that sample size to be very large. Why is that the case? So suppose I administer this vaccine to a group of 10 people. Okay. Now, if these 10 people respond favorably to the vaccine, that's encouraging, right? That tells me that this vaccine might work, but I don't know whether it will work in a large sample, right? I don't know. It's maybe something about just these 10 people that's making the vaccine work and is safe for them. But if I go deploy this on the larger population based on the results of the study of these 10 people, that might result in some disastrous consequences. So what I might want to do in this case is to have a large sample size. The larger the sample size in general, the more confident I can be in the robustness of the results. So if the vaccine actually works in a sample of 10,000 people, I can be reasonably confident that it might work in a population of 1 million people. That the sample size is large enough to give me a measure of confidence that the drug actually works, right? So So in experimental design in general, sample size is one key element of it. The larger you can, the bigger the sample size you can get, the better the results are in general. Okay. And finally, replication. Replication is quality control of the study, right? Replication is the process through which, given you tell me that you conduct an experiment under these conditions, I should be able to replicate the results that you found in your experiment under the same conditions, right? This is a way to verify whether what you're saying is true or not, right? So allows us to keep repeating the study for different groups of people, so that we can independently verify the results, and then we can be reasonably more confident, right? If the results keep holding up in multiple different replications of that study, then we can grow more and more confident that the results are actually not just a fluke. It's not just because of one random quirk of one random study, but rather that it's actually reasonably cogent and reasonably robust, that we can use it to inform something about the entirety of the population. Okay. So 4 key elements of control of an experimental design. If you're going to conduct an experiment, then you want to make sure you control for other variables, for confounding variables, that you employ a certain amount of randomization in your experimental design. Then you want to make sure that the sample size is sufficiently large, and then allow for the fact that you should be able to replicate this study and get similar results. You might not get exactly the same results. No one is asking for exactly the same results, but they need to be very similar, right? All right. So here's an example of an experiment, and the question is, let's see if this experiment is good or not, whether this experimental design is good or not. So this new company has come up and they are testing this new gum. This is effectiveness of a new gum to help people quit smoking, right? And so they're like, okay, so let's do this. The experimental design is the following. So the company first identifies 1,000 adults who are heavy smokers. They're divided into blocks according to gender. So all the male smokers are in one block, all the female smokers are in one block. After 2 months, the female group has a significant number of subjects who have quit smoking versus the male group. Okay. What is a possible problem with this study? Okay. One possible problem straight away that we can identify is that you went to the block design where you first divided the people up into male and female blocks and then randomly assigned them within that block. Okay. Problem with this is that it could be the case that this gum is more effective with women than it is with men. We haven't ruled out that possibility just yet. Okay. And that's the problem. These groups are not similar, right? The groups that we are comparing might not be similar, that the new gum might have a greater effect on women than men, or the other way around. And we haven't ruled that out. And one suggestion for us to rule that, make sure that's not the case, is that the subjects can be divided into blocks according to gender. That's fine. But then within each block, we need to make sure that we randomize, right? In whether the men which of the men who are in the treatment group or in the control group, we need to randomize on that level in order for us to be more confident in the results of this experiment, right? Because if you just put men and women in two groups and then give the one group the gum and not the other group, it might just be the fact that one group is more affected by this intervention than the other one, and we need to rule that possibility out. And for that reason, we might have to employ another level of randomization in the experiment, in the technique. Okay. All right. The last thing that I want to talk about in this session is around sampling techniques, right? And it goes back to the original story that we've talked about, right? So in the original story, what do we have? So the end goal is to study and say something meaningful about the entirety of the population, but it might not always be possible for me to be able to do that, right? So in that case, then I might want to collect a sample out of the population and study that and use that as a stand-in for the underlying population, right? So how do I form this sample? What techniques are available for this sample, for forming the sample? The simplest way of forming a sample is what we call a random sampling, right? Where I just throw a dart into the population, wherever the dart lands, that person is inside the sample, and that's how. And I keep repeatedly throwing darts like that at random, and each member of the population has an equal chance of being selected, right? So that's the easiest way for me to form a sample is just randomize. I just throw darts and then pick people out of the population at random, and all the people that I pick are now part of my sample, and I use that sample to study. Okay. Now, this is refinement on this technique is what we call a simple random sample, where what I do is first I throw darts into the population and then I form a sample. Okay, so suppose my sample size is going to be 50 people. In each sample, there's going to be 50 people selected. So there's a population, I throw darts into a population, I pick 50 people and put them in the first sample. Then I go back and throw 50 more darts and collect 50 more people and put them in a second sample, and then throw 50 more darts and put them in the third sample. The reason for doing that, and the sample that I choose for study is then chosen randomly. Then out of these 3 samples that I have, I pick one of them at random and use that to study. This is a slightly better way of doing things because I might just end up with a sample, even a random sample, which is biased in some significant way, right? Even though I'm just throwing darts at random, suppose the darts keep picking out people who are very alike in or very different, that particular sample is biased in some fundamental way. For instance, again, suppose 50% men, 50% population women, if that is the population split, suppose I throw darts into the thing and I pick 50 people, and it turns out purely by random chance that 48 people are men and 2 people are women. Now if I use that sample to study, if that's the only sample that I have, then I might get very biased results. So instead what I do is that I repeatedly sample from that population. This is repeated sampling from that population, and the sample that I want to study is completely chosen at random. That makes it less likely, much less likely that I end up with a biased sample and then I get biased results out of it. Okay, so that's the sampling technique that we'll call a simple random sample. There is a next a more refined technique, which is what we call a stratified sampling, right? So this is where this is basically one way for us to make sure that we get a more or less a representative sample, right? So in a stratified sample, we first divide the population into groups, right? We know that different groups behave differently, so we define them differently. For instance, we want to make sure that we get representation from all income levels in the economy, right? So we might divide the population up into low income, middle income, and high income. Instead of just randomly throwing darts into the population, hoping that we get like some low income, some middle income, and some high income households in the sample, we deliberately first divide the entire population into groups and then make sure that we sample from each of these groups, right? So stratified sample is that you divide the population first into groups or strata and then select a random sample from each group. Okay, so a stratified sampling technique basically makes sure that we get some entries from the low income, some data from the middle income, some data from the high income. So the sample that we form is going to be kind of more representative. This is one way to guarantee that sample is at least somewhat more representative relative to just throwing random darts into the population and hoping that you get a representative sample. Okay. Cluster sampling is where it's the basic idea is still the same, where you divide the population up into clusters, into groups, but you sample from one or more of these groups, but always leave one of them out, right? But you never sample from all of the clusters. this cluster that you leave out becomes the baseline case, right? So suppose there's a zip codes in Westridge County, and zone 1 consists of a lot of very high income neighborhoods, right? But you're not concerned about high income neighborhoods. The policy that you're trying to implement, you want to know what middle class people and low income people think. So you might want to leave out sampling people from this high income neighborhood and instead focus on just sampling the other three things. So between a stratified and a cluster sample, the key difference is whether we are going to collect information from all of the groups or whether we're going to leave some of the groups out. If you're going to collect from some information from all of the groups that we divided the population into, then we have a stratified sample. If you leave some of these groups out from the sample, then we have what we call a cluster sample. Okay. Then there is systematic sampling. That's one easy technique. This is basically where you choose the starting point at random, and then you basically sample in a systematic way from there, right? So if I want to conduct a survey of households, the starting house that I choose could be chosen completely at random, and then I go to every 10th house. This just makes surveying much easier, because I send a person out with a clipboard to collect these responses, and I tell them start at house number 45 and then survey every 10th household from there, or every 100th household from there, some random number that I pick, right? So that makes sure that I cover enough of the neighborhood, because if you think about it, if I send this person out and say collect information on 10 households, they might just collect that information from the same neighborhood, because that makes the job easier. I just go from house to house and house to house. 10 houses, done. I've knocked it out of the park. But those 10 houses, the people who live in those 10 houses might be very alike from each other. They might be sorting behavior within that area, within a small group, and then you might have a very biased sample. So instead, to avoid that, you tell them that okay, you start at this house, but collect data from every 10th, 20th, 50th, whatever number you want, house from there. So that makes sure that you collect data from a wider swath of people inside that area. Okay. All right. So here's a couple of examples to identify whether what kind of sampling technique is you're using. So here's the first one. So you divide the student population with respect to majors and randomly select and question some students in each major. Okay. Straight away, what kind of sampling is this? It's either going to be a cluster or a stratified sample, right? Because you're dividing the population into groups based on the majors that they've chosen, and then you're sampling from these groups. And you're going to sample from each major, some from each of these groups, so which means that we have a stratified sampling. Right? So because we are first dividing the population into groups and then making sure that we sample from each of these groups, from every single one of these groups, we have what we call a stratified sample. Okay? So here's the second one. You assign each student a number and generate random numbers. You then question each student whose number is randomly selected. Right? So there is 2 levels of randomization in here. There's the simple random sample. Okay? So each student is now a sample, and each sample has an equal chance of being selected, and each student has equal chance of being selected. This is 2 levels of randomization that we talked about. So we have a simple random sample in this case. Okay. So that's where I'll stop with the session for this week. So this is a quick introduction to statistics, some definitions, some key ideas and principles of statistical design and study. And if you have any questions, leave them in the comments below the video, or send me an email, or see me in office hours. I'm happy to help. But that's all we'll do for this week, and in the next week we'll pick up where we left off and start talking about the technical details of statistics, where we begin to talk through the details around inferential into descriptive statistics. Right? All right, so thanks everyone for listening, and I will see you in the next one.